Hey, welcome to the free Westport Astronomical Society Science Lecture Series. We do this every month, and we've been on Zoom for quite a while, as Shannon had mentioned earlier, and hopefully we can get back to having live people in the classroom again. I hope that's coming up. And as we mentioned, May 18th, Thierry Legault will be joining us, capturing the most elusive objects in the solar system. He is a fantastic astrophotographer. So he'll be zooming in from France, and that may be our last Zoom call for a while. We'll see. But thanks to everybody on the Zoom conference tonight. We've got the live stream going on the YouTube channel and everybody that came from Meetup. So thank you for this. And we'll do it again next month. And let me introduce you to our speaker tonight. Dr. Lisa Upton received her PhD in physics from Vanderbilt University in May of 2014. And for her PhD dissertation, which was characterizing and modeling magnetic flux transport in the sun's photosphere and determining its impact on the sunspot cycle, Dr. Upton developed, along with David Hathaway, a cutting-edge surface flux transport model, which is called the advective flux transport, or AFT. And back in September of 2014, Dr. Upton, she moved out to Colorado, and she began working for the Space Systems Research Corporation, which is SSRC, and held a role as a visiting scientist at the High Altitude Observatory in Boulder. And in the spring of 2017, she took a couple years off, took a sabbatical from SSRC to accept an NSF postdoctoral fellowship for 2 years. And in the fall of 2018, NOAA and NASA convened the Solar Cycle 25 Prediction Panel, which is crazy, as we're seeing with Solar Cycle 25 now. Is it coming earlier or not? Well, we'll find out. And together with one of her representatives, she was asked to serve as the NASA representative co-chair of the panel alongside Doug Biesager from NOAA. And together they led a panel of 12 to conduct a survey of forecasts for the amplitude and timing of Solar Cycle 25 in order to obtain and recommend a consensus forecast. So I'll let Dr. Upton explain everything else. So please welcome Dr. Lisa Upton to the April 2021 free Westport Astronomical Society Series lecture. Dr. Upton.
Thank you so much. I appreciate the invitation to be here and talk to you all today about a subject that is very near and dear to me. Let me go ahead and start sharing my screen. And also, I have to say, Franco, those photos were amazing. I am so impressed. Beautiful, beautiful, beautiful. All right, so let me share my screen and we'll get started. Okay, are you guys seeing my slide presentation here?
Yes.
Okay, fantastic. Okay, so today I'm going to talk to all of you about the sun, space weather, and the solar activity cycle. As he mentioned earlier, I'm with Space Systems Research Corporation and also was the co-chair of the Solar Cycle 25 Prediction Panel. So to give you just a brief outline of what I'm going to talk to you about today, I'm going to start with a really an introduction to the sun, really basic level, just to kind of get everybody on the same page. I'm going to go into a little bit about space weather, some of the things that can impact our space environment. I'm going to talk to you about the solar cycle, tell you what that is, and then tell you about our prediction for Solar Cycle 25 and tell you how we've been doing so far. And then we'll follow up with questions. So let's get started with the introduction to the sun. So when I first started learning about the sun, when I came into it, I was really interested in astrophysics, and I wasn't really quite sure what I wanted to do. There was all these very exciting things, galaxies, black holes, things that I was interested in studying. But the only thing that was being studied at the university I was at was the sun, and I thought, wow, the sun's not that interesting. It's pretty boring. It's just this big ball of gas floating across the sky. It rises in the morning and it sets at night. But boy, was I wrong. The sun is actually an extremely dynamic place. There is a lot going on there. And so it's actually a very exciting place to study. So let me get started by introducing you to the sun. I'm going to start by talking about the structure of the sun, the various different layers. We start at the interior, at the core, and work our way up to the corona. So the core is the place where the nuclear fusion takes place. This is at the very center of the sun. It's inside the first 0.25 our sun, or the radius of the sun, so the first quarter of the sun. It has temperatures on the order of about 15 million degrees at the very center, and that tapers off to about 7 million by the time you get to the top of the core. This is where the nuclear fusion goes on. The most prolific fusion reaction is the proton-proton chain. This is where the helium is produced to turn the hydrogen into the helium. And there's also the CNO cycle. This is where carbon and nitrogen are converted to oxygen. Above the core, we move into the radiative zone. This is a place where there's energy is being transported by radiative processes. This region spans from 0.25 our sun to about 0.7 our sun. And the temperature drops from a balmy 7 million degrees down to a relatively cool 2 million Kelvin degrees. This region of the sun is so dense that photons can only travel a very short distance before they're scattered and reabsorbed. So it really takes an individual photon on the order of about 1 million years to leave this zone and move out into the outer layer. So when a new photon is produced in the sun, it takes a long time for it to get to us. Moving out, we move into the convective zone. This region, the energy is transported by convective motion. This is the region that spans from about 0.7 our sun all the way up to the visible surface. And here the temperature drops from about 2 million Kelvin down to about 6,000 Kelvin. This is where most of the heavier ions exist. They hold on to some of their electrons, and this makes the region much more opaque. So it's really hard for radiation to get through. And this traps in the heat, which causes this big temperature gradient that makes the fluid very unstable. And so the most efficient way for that heat to get out is to start boiling or convecting like a pot of water. And so you get these very turbulent motions, just like in the video on the bottom right. Moving out, we reach the photosphere. This is what we refer to as the surface of the sun, although it's not really technically a surface. It's actually more like a layer about 100 kilometers thick. It's nominally at 1 our sun, 1 radius of the sun. The temperature here is a cool 6,000 degrees, and it has an optical depth that falls off very rapidly. And so when you look at the sun, you're going to see this feature called limb darkening. And this is where, the sun looks very bright near the center of it. As you go off to the edges, you're seeing through more sun. And so you get this darkening effect on the outer edges. We can also look at the photosphere with different wavelengths, and this allows us to sample different structures and different depths in that photosphere. Above the photosphere, up in the atmosphere, we get to the chromosphere. This region is somewhere between, runs from about 6,000 to about 15,000 Kelvin. It gets its name because it has, if you take an image of it, it kind of has a red appearance during the eclipse. And this region is optically thin. So this is where the light is really too faint to be seen unless you're looking at it through an eclipse, or you're looking at it with a telescope with an occulting disk. So it's really best viewed during an eclipse. And moving out even further, we reach the transition region. It's called the transition region because the temperature very rapidly changes from 10,000 Kelvin up to 1 million Kelvin. This rise in temperature causes carbon and oxygen and silicon to ionize, and this is what produces UV light. And so the transition region is very large temperature gradient. It's almost a step function here, as shown in the plot. And above the transition region, we finally reach the outermost layer of the sun. This is known as the corona. The temperatures are on the order of about 1 million to about 3 million Kelvin. And that's really surprising. When we think about something that's emitting or radiating heat, typically the further you get away from that heat source, it's going to cool off. Like you would, if you're now around a campfire, if you want to cool off, you move further away. And so with the sun, it actually gets much, much hotter up in the corona. As I mentioned before, the surface is only about 6,000 Kelvin. And so to go from 6,000 Kelvin to several million of Kelvin is really quite the puzzle. And this is referred to in solar physics as the coronal heating problem. And so there's a lot of interest in studying how does all that heat, how does all that energy get into these outer regions of the corona. This is also what you're going to see when you look at an eclipse. If you saw the eclipse a few years ago, you might have seen similar structures, these bands coming out of each end, forming these kind of cusps on each side. So instead of an outer region to the corona, you can see that it just kind of gradually tapers off into an outward stream of moving particles known as the solar wind. So there's not really an outer boundary to the sun. Again, we can look at it in various different wavelengths, and this allows us to sample different elements and different structures, as you can see on the image at the bottom. So let's move into a discussion about space weather. First off, what is space weather? Space weather refers to the conditions on the sun and in the space environment that can influence the performance and reliability of spaceborne and ground-based technology, and can endanger human life or health up in space. And it can actually impact us here on Earth as well. So let's talk about what is space, what kinds of space weather are there? The most often when we talk about space weather, we're going to be talking about the solar wind. This is this constant stream of particles in the corona that are constantly being sent out into the heliosphere. The solar wind is supersonic with the slow wind on the order of about 300 kilometers a second. And then the fast solar wind, which comes out over the poles at about 800 kilometers per second. These high and low speed streams, they interact with each other, and they alternately pass by the Earth as the sun rotates. And this interaction with these oscillating streams actually causes fluctuations in the Earth's magnetosphere and can interfere with our satellites and cause disruptions with the satellite grid and things like that. So these variations can produce what are known as geomagnetic storms, and that's these interaction with the Earth's magnetosphere. So moving on to sunspots, these are probably the most well-known features of the sun. These are cool, dark regions that appear on the surface of the sun. And this is essentially where strong magnetic fields are emerging through the sun. And as they emerge through the sun, because the magnetic fields are so strong, they inhibit the transport of heat. And so it causes the center of these sunspots to be relatively cool compared to the rest of the surface of the sun. Sunspots usually occur in groups known as active regions that typically have a leading polarity where the magnetic field emerges and a following polarity where it then goes back into the surface of the sun. Active regions typically last anywhere from a few days to a few weeks, and they were originally used to determine that the sun rotates in about 27 days. For a solar physicist, we often refer to this as a Carrington rotation. So if I say Carrington rotation, this means one rotation of the sun. Sunspots also have a characteristic tilt known as Joy's law tilt, and it's tilted such that the leading polarity spot is always or is usually closer to the equator than the following polarity spot. And then also has this property known as Hale's polarity. And so this property means that the sunspots have opposite polarity when you go from the northern hemisphere to the southern hemisphere. So if you have a positive spot leading in the northern hemisphere, the spots in the south are probably going to be leading with a negative polarity. And then this polarity also changes from one solar cycle to the next. We have these beautiful images of coronal loops. These are just gigantic features on the surface of the sun. So as this magnetic field emerges from the sun, it becomes, the plasma follows these magnetic loops and they become very hot. And as they become hot, they obviously emit light in the various different wavelengths, and they form these beautiful arches known as coronal loops. These structures are associated with the closed magnetic fields of the active regions, and they typically last for anywhere from a few days to a week. To a few weeks, but they typically also change very rapidly. You'll see a lot of change in them. Coronal holes, another feature of the corona, are very dark regions that are typically observed over the poles. These regions are associated with open magnetic fields. So whereas with the active region, you have a closed magnetic field that comes out of the sun and then immediately submerges. With the open magnetic field, it's really just expanding way out into space to very long distances, and then it comes back around eventually and comes back into the opposite pole. So we call these open magnetic field lines. And like I said, they're typically found at the poles, but as the magnetic field on the sun becomes much more complicated, they will dip down into the lower latitudes closer to the equator. The high-speed solar wind is also known to originate from the coronal holes. You guys saw some great pictures of prominences, also known as filaments, earlier today with Franco's beautiful pictures. These are basically dense, cooler, almost like clouds of material that are suspended over the surface of the sun by the sun's magnetic field. They typically remain in a quiet state and just kind of lay about, linger there for several days. But if the conditions are right, they can erupt and rise off of the sun and send a huge amount of plasma and energy out into space. One of the most, probably the most significant sources of space weather is known as solar flares. These are massive explosions on the sun, and these can often trigger an eruption of a prominence. But these are massive explosions that release a large amount of energy. They produce a sudden flash or brightening in the flare, and these are typically located near active regions. They eject electrons, ions, atoms out into the corona and into space. And the first observation of one of these flares was on September of 1859. And it was actually a very well-known event. It's referred to as the Carrington Event. Remember that name, it's really significant. I'm gonna come back to it later. But basically what happened was there was this solar astronomer named Richard Carrington, and he loved looking at the sun, watching these sunspots move on the sun. And he was really, just checking out his sunspots for the day. And all of a sudden he noticed this one sunspot he was looking at got very, very bright really quickly. So he went to run and tell his neighbor about it. But by the time his neighbor came back, it had kind of dissipated. Like I said, stay tuned for the rest of that story. It gets really interesting. Okay, so coronal mass ejections. These are just phenomenally huge, almost unimaginable. You can see that they can get almost as large as the sun itself. So these are large bubbles of gas that are threaded with a magnetic field, and they can erupt and eject just a massive amounts of plasma and energy out into the solar system. And so if you can imagine, as we talked about the scale of the Earth relative to the sun, I mean, the Earth is on the size of one of these little granules on the surface of the sun, one of these little bright or dark dots that you see on the surface of the sun. So if you have one of these coming towards the Earth, it can be a really big deal. Fortunately, we have our Earth's magnetic field to protect us. Although the sun's corona has been observed during total eclipses, it wasn't really, the existence of coronal mass ejections wasn't really known until the space age. And when we were actually able to really study these features, really actually see these features continuously and watch them erupt and evolve. And so they're relatively new to the solar physics world. So why does all of this matter? Why do we care here on Earth? Well, as the charged particles from the solar wind are funneled into the poles, into the Earth's magnetosphere, they collide with the Earth's atmosphere. And this forms a beautiful phenomenon you've probably heard of, and maybe some of you have been lucky enough to see, called the Aurora. And so with very extreme solar events like a flare or a CME, it's bombarding the Earth with just an intense amount of plasma and energy. And as this energy is funneled into the Earth's poles, they can cause damage to satellites that disrupts communications and could even destroy power grids. So going back to the Carrington event that I was telling you about earlier, so this event that Richard Carrington observed was a white light flare. And we know from studying the history books, looking through various different records from monks and Chinese astronomers, people from all over the world that happened to be watching around that time, we know that it actually produced a massive CME, one of the largest on record. And that massive CME just so happened to be directed at Earth. And so when it hit the Earth, it created this geomagnetic storm. This solar storm was so strong, so powerful, that the aurora, which we know are typically restricted to polar regions, it's very, very rare that it dips down into the United States or much lower than that. But this particular solar storm, this Carrington event, was so powerful that the aurora were able to be seen around the world. They were visible as far south as Cuba and Hawaii. They were so the aurora was so bright that the miners here in Colorado at that time that were out mining for gold up in the mountains, it was so bright that they thought that daylight was coming. So they actually got out and started breaking camp, starting breakfast, because this aurora was just so intense. So if we had one of these really massive storms, such as the Carrington event, directed at the Earth, the impact on our infrastructure would just be huge. These solar storms would have the power to disrupt power grids. They can cause power surges that can destroy transformers. And there was a study done a few years ago that found that if there was such an event, if we weren't adequately prepared, that such an event could reach trillions of dollars with a potential recovery time of 4 to 10 years. So we know how bad how bad it is if we have a hurricane or something that knocks out our power for a few days or a week. We get pretty miserable pretty fast. But if you can imagine something like this disrupting your power for 4 to 10 years, that's just really difficult to think about. And so there's a lot of interest in studying this space weather and being able to predict space weather. So in that vein, let me tell you a little bit about the solar cycle. So the solar cycle was first found by observing the number of sunspots. This was Samuel Heinrich Schwabe. He was the first astronomer to track the number of sunspots as a function of time. And when he did this, he found that the number of sunspots varied with a period of about 11 years, 10 to 11 years. And then as new features of the sun have been discovered, it was found that they also vary with the sunspot variability. And so now the sunspot number, the count of sunspots on the sun, is actually the metric that we use to quantify the level of solar activity. And we can see this very clearly if we take a series of images of the sun over an 11-year span. You can see that the sun starts out very, very boring. There's not a lot going on. All of a sudden, you start to see some active regions emerging. They build up. You get more and more active regions distributed across the equatorial regions. And then eventually, they start to fade off until we get to a very quiet state again. We can look at this also with magnetic maps of the sun, and we can see that these magnetic features on the sun, the sunspots, why these sunspots are commonly accepted measure of the solar activity. So you got these beautiful magnetic regions, again, starting off with a relatively blank sun, not a whole lot going on, moving up to a lot of activity and then fading off. So if we count, if we look back at the historical record, sunspot counts for the last few hundred years, we know that there is, that we have about 24 cycles in counting. So we're just now starting solar cycle 25. From all of this data that we have, we know that the sun activity on the sun is periodic with an average cycle that lasts about 11 years and with a peak sunspot number of about 180. If you're talking about sunspot numbers, please be careful. There was a version 1 that was being used that was about 0.6 what the current sunspot number is. So there was a recent initiative to go back and restudy the records and recalibrate the sunspot number. And so on the newest sunspot scale, the average sunspot cycle has an order of about 180, as to opposed to about 100 if you're using a sunspot number version 1.0. So as I mentioned, sunspots, they typically appear near the equator. They occur in these two bands on either side of the equator. And as the solar cycle progresses, these bands drift closer and closer to the equator. And so when you plot these active regions as a function of time, you see that it forms this really beautiful picture that kind of almost looks like the wings of a butterfly. And so the name of this kind of plot is called a butterfly diagram. We also see that the solar cycle typically overlap by about 2 to 3 years, although that wasn't the case for the last solar minimum, and it isn't really the case for this current solar minimum, but I'll come back to that. If we plot the sun's magnetic field as a function of time, we see that in addition to the magnetic field in the active regions, the sun also has polar magnetic fields that form a weak dipole. And so these are the streams coming out of the pole that you would see in a total eclipse or with a coronagraph, these polar streams, and that this weak dipole, the polarity of it reverses about the time of solar cycle maximum from one cycle to the next. We also know that if we plot the polar field strengths as a function of time, that the polar fields observed after the solar cycle 23 were about half as strong as those observed for the previous 2 cycles. This was followed by an extended solar cycle, cycle 23-24 minimum, and cycle 24, which proved to be one of the weakest cycles in at least 100 years. So try to get at this and try to understand what produces this evolution of the polar fields, we really need to look at the motions of the plasma on the sun. So let's start with the differential rotation. So differential rotation basically refers to the fact that the sun's equator rotates much faster than the poles. This happens because the sun is not a solid body. It's a fluid, like it's a plasma, which moves more like a fluid. And so the equator, the sun rotates very, very quickly and much slower at the poles. It takes about 25 days for one rotation at the equator and about 35 days at the poles. If you average it out, it is about 27 days, which is what we refer to as a Carrington rotation. So in addition to this east-west flow, we call the differential rotation, the sun also has a north-south flow. This is called the Meridianal Flow. This flow is poleward at the surface. So moving from the equators, it moves up towards the poles, and it's very, very weak. Whereas the differential rotation is on the order of about 200 to 250 meters per second. The Meridianal flow is only on about 10 to 20 meters per second. And because of this, it's been very difficult to measure this meridianal flow. And in fact, there's still areas of the meridianal flow that we're not fully sure of and that we're very actively trying to study and understand. We expect that the meridianal flow is going to turn equatorward at some depth. And the other thing that we're not completely sure about is what exactly happens at the poles. There have been suggestions that there might be counter cells at the pole where instead of going poleward, it might start moving equatorward. But this has been very controversial in the field, and it's something that we're really actively studying. By the time that it gets to the poles, it's getting very close to zero, a meter or two per second. And as you can imagine, that's really challenging to measure these kind of velocities, particularly when you're trying to measure this on top of the convective flows. So if you look at the surface of the sun, you see some of the images that Franco showed earlier. You see all these little specks. These are the convective cells that occur because there is such a large temperature gradient in the sun that causes the plasma to boil, kind of like a pot of water. And so the plasma just rises up, it rises up and falls just like a pot of water. As I said earlier, this is the most effective way to transport heat. And what happens is that the magnetic field that's getting pulled off of the active regions, it kind of gets distributed into the boundaries of these convective cells. These convective cells aren't the only convective cells. There's actually a whole spectrum of convective structures that exist on the sun. At the smallest scales, you have the granules. These are about 1,000 kilometers wide. They have velocities on the order of 3,000 meters per second, but they only live for about 10 minutes. As you go up on the spectrum, the most dominant feature on the convective spectrum of the sun are referred to as supergranules. These are what you will see if you look at a Doppler image of the sun. And these have lengths of or diameters of about 30,000 kilometers. The speed slows down. They only move on the order of about 500 have velocities on the order of about 500 meters per second, but they live a little bit longer. They last about a day or two, a few days. And then as you move to the largest size convective structure on the sun, these are the convective structures that are going to span the whole convection zone. And they have sizes on the order of about 200,000 kilometers, significantly slowed down to velocity of about 10 meters per second, but lifetimes of several months. These are referred to as giant sails. And these have been theorized for several years, probably about 4 decades or so. But it's only just recently that we've actually been able to start to observe these. And this is actually a part of a work that I've been working on with David Hathaway to try to nail down these features. And so this last figure is from a paper that we had in Science back in 2010, our first observations of these giant cells. They're still very controversial in the field, and so we do still have a lot to learn, but they can tell us about how the motions of the interior of the sun move. So if we put all of these different pieces together, we get something that looks like this this video that I'm showing. Oh, I thought it was going to keep going, but let's see if I can go back and play it again. And what we see here is there's an active region. This is this bright blue and yellow region on the bottom right. This is where an active region or a sunspot. And what is happening is you have the turbulent convective motions that are surrounding it. It's shredding off the magnetic field from that active region and redistributing it into the magnetic, to the surrounding convective network and forming this magnetic network on the surface of the sun. From there, it's then transported by the axisymmetric flows, the differential rotation, the Meridianal flow, and the convective motions, and really just distributes it all over the sun. And so by putting all of these different pieces of the puzzle together, there was a solar physicist named Babcock back in the 1960s that created this phenomenological model to try to understand what causes the sunspot cycle. And so if you look at this figure on the bottom left, panel A, we'll start there. This represents a solar minimum. This is when the sun is in a very dipolar configuration. It has this very weak axisymmetric dipole. We refer to this as a poloidal field. And these magnetic field lines, that kind of look like the coronal image that we saw earlier. These magnetic field lines submerge into the sun and are threaded through the convection zone. So as they're threaded through the convection zone, they are sheared by the differential rotation. That essentially the differential rotation wraps this magnetic field around the equator of the sun. And when it does this, it becomes it causes the magnetic fields to become stronger. And when they become stronger, they become buoyant and they rise up to the surface, forming the sunspots or the active regions. So that's what you see in panel C there. These active regions emerge with a characteristic Joy's law tilt and the Hale's polarity. And so as the video I just showed illustrated, this magnetic flux is then shredded off the active regions of sunspots and it's spread out by these convective motions. And it does it in such a way that the leading polarity spots tend to cancel with the lower latitude spots and eventually across the equator, leaving some residual following polarity spots that are flux that happens to be the opposite polarity of the poles. And so this reverses the sun's polar magnetic fields and builds up a new poloidal field with the opposite polarity. And that brings us back to panel A. And so this cycle repeats over and over again. So if we, so Babcock's model is widely accepted as the underlying mechanism behind the solar cycle, but the finer details aren't very well understood. And so there's still a lot of research into this area. Most solar physicists, however, will agree if you plot that the solar minimum, that the poloidal fields, the polar fields at solar minimum are the seeds to the next cycle. And so if you plot the strength of the polar fields as a function of the amplitude of the next cycle, you'll see that there's this very nice correlation here. And so we've got this very nice indicator of what the next cycle would be by looking at these polar fields. So let's look at some solar cycle 25 predictions. As I discussed earlier, I was a co-chair of the Solar Cycle 25 prediction panel. Back in December of 2018, we put out a call for predictions all across the world to try to assess what would happen with Solar Cycle 25. We accepted predictions through February of 2019, and then we also conducted an extensive literature review looking for predictions. We gathered the panel of 12. We were charged with predicting the onset of solar cycle 25, or the solar minimum. We were charged with predicting the intensity and the timing of solar cycle 25. And then if possible, also to try to provide some insight into the hemispheric asymmetry, F10 centimeter flux, and possibly predict solar flare and CME rates. So we got everybody together. Overall, we had about 61 predictions that we evaluated. We kind of divided them up into different classes: climatology, spectral, statistical, machine learning. These are all numerical type methods. This is one class of predictions. Then there are the physics-based methods. These are things that look at the polar fields as a precursor to the solar cycle. And then also surface flux transport models and dynamo models, which try to extend those predictions of the polar fields by simulating the motions of the magnetic field on the surface of the sun to try to figure out what those polar fields will be 3 to 5 years in advance. And then there was an other category where we put things that just weren't really any of these particular categories. We used the new Sunspot number, so we had to make sure to scale all of the predictions that were in Sunspot number version 1 to Sunspot version number 2. And so if we look at the predictions, all of the predictions that we look at, there's actually quite a bit of agreement. They're all kind of on the lower end of the solar cycle spectrum. There is still a little bit of variability, but as a panel, we tended to agree that the methods that use the physics-based methods that looked at the polar fields, the polar field precursors, the surface flux transport dynamo models, the dynamo models, the ones that use the polar fields to get at the predictions, were probably had been the most successful in the past, and probably were going to be most likely to tell us what's going to happen with solar cycle 25. So taking a look at those sets of predictions, you can see that they all kind of lie on the order of about 100, maybe 110. There's a little bit of scatter about that, but in general, indicating that we're going to have a fairly weak cycle. And so these prediction methods, again, these are kind of the second half of that dynamo model that I told you about. This is the conversion of the toroidal field that's emerging in the sunspots to the poloidal field, using these models to predict how this flux is going to evolve on the surface of the sun to arrive at these polar fields to get these predictions. So as a whole, our consensus forecast was that solar cycle 25 is going to be very similar to cycle 24. We predicted that the cycle 24-25 minima would occur somewhere between somewhere around April 2020 plus or minus 6 months, and that solar cycle 25 will have a peak of about 115. As I said earlier, the average is 180, so this is a relatively weak solar cycle, and the solar maximum is going to occur somewhere around July of 2025, plus or minus about 8 months. So again, we're expecting a solar cycle 25 to be very similar to solar cycle 24. So one of the interesting things is that if you look at the recent history of the sunspot numbers over the past 4 or 5 decades, you see that there's kind of this downward trend in the solar activity. If we start at solar cycle 25, down to 23, down to 24, there was a lot of speculation that 25 was going to carry on this tradition and we were going to dive into a period of very little or no activity. These are commonly referred to as a Maunder type solar minimum. But with solar cycle 25 expected to be similar to solar cycle 24, this would mean an end to this downward trend. So the sun is not broken. There's no indication that we're entering another Maunder type minimum. The cycle is still stronger than a Dalton type minimum. And what we may actually be entering is almost an inflection point. It'll be very interesting to see if after solar cycle 25, if the sun starts to pick up again and we start to see an increase in solar cycles strength again. Not to say that we can disregard what's going on in the sun. Extreme space weather events can still happen near a solar minimum. And in fact, back in March of 1989, there was a huge storm that impacted you guys as neighbors over there in Quebec. This solar storm knocked out the power grid in Quebec. It was one of the most extreme storms in the space age. I think the power was out in Quebec for on the order of about a week. There was also a solar storm in 2012. We were very, very fortunate here on the Earth because this storm actually didn't come towards the Earth. It went the other direction. But this solar storm included an ultra-fast CME. And the measurements that we have suggest that if it was directed towards the Earth, it may have been very akin to this Carrington type event, this Carrington class storm that I mentioned earlier, which would be devastating to us here on Earth. So we're very lucky that it went the other way. And so the point is that even with weak solar cycles like solar cycle 25 or during the decline of a cycle when the sunspot numbers are getting very low, you can still have these very strong storms that can really impact our space environment. So let's take a look at how are we doing so far. How does the activity on the sun look? So if we look at the sunspots, and this is a plot that I found on the web that it's very nicely done by Janssens, and what it does is it shows the position of the sunspots. And so these little spots, let's see if I can get my cursor here. These spots right here and here, these are the very first spots that we're seeing for solar cycle 25. And what I want to point out is that if you notice, these spots are occurring at much lower latitudes than the early spots in other cycles. And this is very common when you have a very weak solar cycle. It takes the dynamo a little bit longer to get that magnetic field twisted around the equator and build up a strong enough magnetic field to emerge these sunspots. And so by the time this happens, the dynamo is usually operating at much lower latitudes. And so this fact that these early sunspots are occurring at generally lower latitudes than they have in the past few solar cycles is an indication that we are kind of on track for a very weak solar cycle. Another thing that we can look at is the number of spotless days. So very weak cycles, as I said, it takes a little while for the sun to kind of ramp up and start the active region emergence process. And so what happens, rather than having this overlap in the solar cycles as we've had, back in solar cycle 22, 23, and earlier, you'll have these extended periods of very weak or no activity. You'll have spotless days that'll go, hundreds or a year, hundreds of days or even a year. And so if we plot the number of spotless days as a function of time, you see that that the minimum between solar cycle 24 and 25 had a large amount of spotless days. So this is another indicator that we're in for a weak cycle. Again, this extended minimum that kind of goes along with that, another indicator that we're expecting a weak cycle. So weak cycles are typically preceded by these long, deep minimums like we currently have been experiencing. But we do see that has started to turn around. We're actually starting to get those active regions emerging again. And once the active regions start emerging again, we can start to take a look at how well we did at minimum. We're not able to determine the actual timing of minimum until about 6 months after it occurs. And this is because to calculate the minimum of the solar cycle, we actually do a 13-month running average. And so you really have to get about 6 months past minimum before you can really say for sure that it occurred. But we've had a ramp up of activity, and we can see that the timing of minimum actually occurred in December of 2019. If you recall, our prediction was that it would occur somewhere between April 2020 plus or minus 6 months. So we're at the very early edge of that prediction. And so the red curve would be our average prediction. But if we readjust our calculations now based on the timing of the minimum, this very early prediction that we had, we see that this curve fits very nicely with the sunspots that we are observing. So yes, we are in fact on track to having a very weak solar cycle 25. It's right on track with our earliest prediction for solar cycle minimum. It'll be interesting to see what happens in the coming years, because the rate that this sunspot activity ramps up is another indicator of how strong the solar cycle would be. So with a much stronger solar cycle, you would expect that ramp up to be much more rapidly than what we're seeing. So with this kind of slow, gradual ramp up, we're very confident that our predictions are on track for this relatively weak solar cycle 25. So if you'd like to keep watching what's going on in the sun, I encourage you to visit my website. This is a website that I created along with David Hathaway. We update these figures about once a month. So our website is solarcyclescience.com. And so there's a lot of information there about the sun, about my area of research, the things that I study. So if you want to learn a little bit more about that, please go there and check it out. You can also visit the Space Weather Prediction Center's website on NOAA, and that's where you'll find the figures like this. It's interesting that NOAA's the organization that's charged with the space weather prediction, but that's just how it happened to work out. So that's the Space Weather Prediction Center at NOAA.gov, and they update these plots fairly regularly. You can also play with looking at our various different predictions. If you go a little bit below what I'm showing on the screen, there's a nice little drop down that allows you to add these different curves, our error estimate curves. And so that's exactly what I did here. I took the curve and the nominal plot, and I added on our prediction for if the solar minimum was 6 months earlier. And so that's that yellow curve that you see added on here. And so you can kind of see the range of variables, the range of activity that we might expect with this solar cycle. But again, with the solar cycle minimum occurring closer to the beginning of our range, I expect that the rest of the solar cycle is going to follow suit. As you can see, the timing of maximum has also shifted a little bit earlier. So I would expect the maximum of activity to occur closer to the late 2024, maybe beginning of 2025, rather than later in 2025. And so with that, I guess I will open it up for questions if anybody has anything they'd like to ask.
Yeah, that was great.
Thank you. Thank you.
Yeah, I think we've got, there's a few questions that kind of popped in. Franco was instrumental in inviting you. So let's have Franco ask the first questions.
Thank you, Franco.
Thank you. That's a fantastic lecture. I learned so much. It's great.
Great.
Thank you. Can you please talk us a little bit about microflares?
It's not really my area of expertise.
Oh, really? Okay.
But I can tell you what I do know. And so from what I understand is what happens is these typically occur around sunspots. And so what typically happens, as I mentioned earlier, that these areas are very dynamic. You've got this turbulent convective motions. It's constantly churning this plasma, and as it does so, it's twisting these magnetic fields, transferring this kinetic energy into potential energy. And what can happen is that these these magnetic configurations can become slightly unstable. And this is almost the same way that a flare would form, is that as you're adding in this potential energy, these magnetic fields become unstable, and they could just snap like a rubber band. If you're twisting and twisting it up, eventually it's going to reach a breaking point and it's going to snap and it's going to release energy. And so my understanding is that the microflares are kind of the same sort of phenomena as you would see in flares, but at a much smaller scale. So instead of the magnetic fields of an active region snapping, that these are the smaller magnetic fields that are surrounding that active region. Now, again, not my area of expertise, so please do your fact checking on that.
Thank you very much.
Kesev Nair had asked a question too. Can you talk to us a little bit about the Parker Solar Probe and what it's been designed for, what its uses are, and how long is it going to be there, and you know what can you tell us about it?
Yeah, absolutely. I'm actually very excited about the Parker Solar Probe. One of the things that's really interesting about the Parker Solar Probe is that it's actually going to leave the ecliptic plane. Most of our solar observations have been restricted to the Sun-Earth line. We do have some instruments that have gone around, circled around the back of the sun and come back around. But again, those are restricted to the equatorial region of the sun. And so by leaving the equator and kind of going up to a little bit of higher latitudes, this gives us an several opportunities, several awesome features. So first and foremost, it gives us another perspective to view the various different structures that I talked about on the sun. In particular, if you're watching a CME, it can be very challenging when you're modeling a CME to only be able to have one perspective. And so you have to make a lot of assumptions about, okay, which direction is it going? Is it moving, up and to the left, or is it kind of moving more towards me? So you have, with only one perspective, you have to make some assumptions. With this additional vantage point, you kind of can almost do like you kind of get almost a stereoscopic view that allows you to have a much more precise view of where this plasma is moving. And so you can model that much better and test your assumptions. The other thing that it does is by leaving the ecliptic, it gets us, by leaving the ecliptic, you can actually view a little bit higher on the poles. With magnetic field measurements of the sun, you're looking at a vector, right? It's not just an amplitude, but it's an amplitude in a direction. And so with the magnetic fields on the surface of the sun, we have to do what's called a radial field approximation. We assume that the magnetic field is radial. We know this is not exactly true. These magnetic fields on the surface of the sun are typically, inclined. And so determining that directionality, it's called the 180-degree ambiguity, is difficult. And so what that means is if we look at magnetic images of the sun, we get a pretty good picture of what's going on at the center of the sun. But as you move out to the limb, as you move out to the edges, those magnetic fields, they're plagued by noise, they're plagued by foreshortening, and these limb effects that I've talked about. And so there's a lot of uncertainty about the magnetic fields in these regions. And as I mentioned before, one of the regions that we're really wanting to know about are these polar fields. And unfortunately, since we're sitting at the equator, those poles are going to be sitting right at the limb. And so by being able to leave the equator, you get a slightly higher vantage point that allows you to kind of study these polar regions with a little bit more detail. Now, that being said, Parker Solar Probe is only going to kind of move up there very briefly. So it'll move up to these higher latitudes. I think it only gets up to about 10 to 15 degrees latitude, but it only stays up there for about 10 to 15 days, which is great for studying an active region while it's rotating on the disk. But for a lot of the things that we want to do to study the solar cycle, we really need observations for a Carrington rotation or more to really nail down, for instance, the Meridianal Flow measurements at the poles. These flows are just so weak. I'm talking about a meter a second per or two on top of this turbulent convective motions, which I told you is on the order of about thousands of meters a second. So it's almost like trying to measure a fly on a race car. It's really not that easy. And so to really get these measurements down, we really need a satellite that's actually going to go over the poles and have a very extended mission over the poles for several months. But Parker is going to allow us to get a better grasp on what exactly is happening on the poles. Again, it's going to add that extra vantage point that's going to allow us to get a stereoscopic view of some of these structures and tell us a lot about what's going on in the sun. So I'm very excited about Parker.
I see that Professor Moshe Guy has joined us here on the panelists. And Moshe, are you there? You have a question today?
Yes. So the crux of my question is the government listening to you, to us, to scientists, and who are they listening to? Let me try to explain my question. Gas companies hire super sophisticated modeler that gives them a warning, which is a split-second warning before an earthquake will reach a certain area. And then the gas company turn off the gas for this area because anyhow, it's going to blow up so if we have one of these gigantic events that will take us 4 years to recover from it, does the government has any authority, any place where they would say, hey, listen, I think you ought to turn off the entire grid of the entire United States and go into darkness for 1 or 2 days because it's going to blow up anyhow and it's going to take us 4 years to recover from it. So let's go into 2 days of darkness. Enormous responsibility. Who makes this decision? Do we have such a procedure to do that?
Just imagine if somebody said to use masks, for 48 hours, how that would go over. How do you think that's going to be, Moshe?
Obviously, it will require somebody more than Dr. Fauci to. No, but seriously, is there a mechanism? Is there, first of all, an authoritative group that the government would listen to? And if they actually make such a prediction, like the one that we had, that the gigantic event that we had, would there be a possibility to turn off the country grid because anyhow it's going to blow up?
Yes, absolutely there is. So I mentioned it earlier, NOAA has the Space Weather Prediction Center, and that's exactly what they are charged with. They are charged with monitoring space weather. Where I do forecasts for the long-term solar cycle forecasts, they are constantly doing near-term forecasts. So kind of like a 7-day forecast like you would see for the weather here on Earth. And so space weather is kind of in its infancy. We're kind of like where terrestrial weather was about 30 years ago. Fortunately, we can kind of piggyback on a lot of what they've learned to help us improve our models and do better at solar prediction. But we're still working on improving it. So what the Space Weather Prediction Center does at NOAA, and that's commonly we call it SWPC, SWPC at NOAA.org. They constantly are monitoring the space weather environment. They're taking a look at, what is the potential for space weather. And I guarantee you, all of the electric companies, the airlines, they all have the phone number to Space Weather Prediction Center. Doug B. Secker, my co-chair at the Solar Cycle Prediction Panel, talks to me all the time about all these calls he's getting from these various organizations. The DoD in particular is very interested in keeping track of space weather. And so that's what the Space Weather Prediction Center at NOAA does. They monitor the space weather. They keep all of the other organizations informed. Anybody, any of the power companies that want to know, they're in contact with the Space Weather Prediction Center. Like I said, all these other organizations, they keep their pulse on it. Now, again, as was mentioned earlier, the real question becomes, if you get put in that situation where you've got a Carrington class event, how effectively can you convince the local governments to follow through. And I think there is some question about that, and I would hope that that enough people would listen, and that we would be able to do that. Certainly, at the moderate space weather level, there are people that are listening. If there's a solar storm heading toward the space station, they tell the astronauts at the International Space Station, hey, you guys might want to get some cover. There's lots of radiation heading your way, and you might not want that big dose. And so, absolutely, there is infrastructure in place to do that. How practically it would get implemented in the case of a Carrington type event is a little up for question, but I have to say that there has been a lot of interest in the U.S. government over the last 5 to 10 years. President Obama created a space weather action plan initiative where they are actively working on trying to answer these questions. If something like this happens, how do we respond? How do we best disseminate that information and get it out? And so that Space Weather Action Plan is a joint effort by several different groups. I think NOAA, the U.S. Air Force, DOD, and there's fact checking, I'm not sure if I'm naming all the right organizations, but that Space Weather Action Plan is what's going to allow us to make those kinds of actions if we need to.
I have a question. What's the predictability of the CME, and what's the time range from when it actually explodes to come to the Earth?
So a typical CME takes about 2 days to get to the Earth. And so, there are people that are actively studying, trying to, CMEs and trying to get better at predicting, how volatile they are, whether they're likely to erupt. So we have that 2 day, essentially a 2 day morning kind of window. But if we can get better at the predictions, we can extend that. And so there are forecasts that they're kind of like I mentioned, like the weather forecast, where you kind of say, okay, well, there's a probability of, maybe 20% that we might have, a flare or CME today. But, in addition to, probability of it occurring, the other questions that have to be answered, as I mentioned, is what direction is it going? And this is where, the fact that the Parker Solar Probe is adding that additional vantage point, that helps us out. And then the other thing that that we have to know about is a parameter called BZ. And so you can think of this as basically the orientation of the magnetic field as it's coming to Earth. So is that magnetic field pointing up or down? And then is the magnetic field of the Earth pointing up or down? And so if they're aligned or not aligned determines how impactful a geomagnetic storm will be. I forget off the top of my head which direction is which. I think if they're oppositely aligned, maybe it's more impactful, but I don't know for sure. But yeah, so this parameter of BZ kind of tells us how geo-effective a solar storm will be. Another thing that you can do on the Space Weather Prediction Center, one interesting thing to look at they have these things called Aurora oval forecasts. And so they take into consideration our predictions about space weather. What is the solar wind doing? Do we have a flare coming into place? And you'll see that these models of the aurora will take into consideration the fact that you've got this flare that's directed towards the Earth, and they will extend that aurora. And so you guys being at a very high latitude, you may have heard, oh, the aurora, we got a solar storm, the aurora is going to dip down to such and such latitude. If you're in this location, you may be able to take a sneak peek out there and view it. And so that's where that comes from, is they take into those considerations.
Yeah, and kind of going on that today too, I saw that we had an M-class hit today. Mm-hmm. And so that over the Pacific Ocean, mm-hmm. there was actually a radio blackout on shortwave, and propagation for ham radio under 20 meters zoomed. So, mm-hmm. if you're on if you're on 40 meters, that's pretty amazing.
Yeah. The ham radio operators are very in sync with the solar physicists. They're constantly monitoring the solar weather. My colleague David Hathaway, he had a few opportunities to go and give talks to some of their groups, and because they absolutely, if there's a large solar storm. What happens is, that magnetic fields, the magnetic fields of the Earth kind of acts as a shield. It's almost like our guardian protector of these solar storms. And for small fluctuations in the space weather, it'll kind of cause it to shrink or expand. And so you can have some fluctuations in where the radio waves are bouncing off the atmosphere. But in the case of a very large solar storm, if it's impactful enough, it will actually cause the magnetic fields to break and magnetic reconnection to occur. And so that will cause the magnetic field to kind of shrink even deeper and cause these radio blackouts like these ham radios operators are experiencing.
We had another question too from Susan Norman. She, Shannon made some shields for my binoculars so I can look at the sun now. So I can see sunspots, and there's actually sunspots to see.
Yeah.
And Susan Norman asked, what is the lifespan of a sunspot in hours and days? Does this change over the sun cycle?
Yes, absolutely. Okay, so if you're talking about a very small sunspot, it's going to last on the order of a few days. A very large sunspot, we had a massive one back, I think in 2012 or 2014, one of the top 5 largest sunspots on record. Again, it can happen in a solar cycle, in a week solar cycle, you just never know. But this very massive sunspots, they last considerably longer. They can actually last for several rotations, 2 or 3 rotations. So that's about 2 or 3 months. On average, an active region is going to last, a week or 2, but they can span anywhere from a few days to several months.
Great. Other pretty cool questions here. How does the heliosphere stay together? If it is inflated, why doesn't it burst at some point? So that's from Rick St. Hilaire.
Yeah. So it's a balance of pressure. So the sun, the heliosphere is formed by the outward solar wind. And so there's this constant stream of particles and energy that are moving outward. And so you probably, most of you have been to the coast, and when you go to the beach, there's always this wind coming in off the ocean, it's constantly blowing at you. And the sun is kind of like that. It's sending out this constant stream of solar wind. There's all this energy moving out into the space. And so that stream of solar wind puts pressure on the environment outside of our heliosphere. And so the edge of the heliosphere is actually defined by this boundary of where this outward pressure from the solar wind balances the inward pressure from the outside of the heliosphere. And so not really a case where it can burst, because it's not like you're going to poke a hole in it and then there's going to be an explosion, because it's just this constant stream flowing outwards. But that's basically how that boundary of the heliosphere is formed, by this constant pressure from the solar wind pushing outwards and going into a hydrostatic balance with the incoming pressure from outside of the Sun-Earth environment from the heliosphere.
This question kind of goes with that a little bit too. It's from from YouTube, and Stephen Schreier, he's hi, viewing this evening from Kalamazoo, Michigan. Excellent presentation. Question: do you have a hypothesis about why the sun's surface temperature increases to millions of degrees? Thank you.
Yeah, absolutely. They've actually been making some really good progress. Again, that's not my area of expertise. I did dabble it a little bit as an undergraduate student. I did study the coronal loops and trying to understand coronal heating from that standpoint. And so there has been a lot of advances in that area. And this kind of goes back a little bit to this question that Franco asked in terms of microflares. And so what they think is happening is, as I mentioned, there's this turbulent convective motion constantly winding up these magnetic fields, turning this kinetic energy into potential energy. These magnetic fields then snap. And so they have these things called nanoflares. They're even much smaller than the microflares. And so they think that these nanoflares that are kind of positioned, around the active regions are constantly being turned up. And so this energy that is being created by churning up these magnetic fields and that energy breaking. They think that the active regions, the coronal loops are a way for that energy to travel up those loops and into the surrounding area of the corona. Again, it's still an area of active research. There's a lot of details that aren't well understood, but this idea of these nano flares just constantly bursting and popping and sending energy into the system and then being traveling up through the coronal loops is kind of I think the leading hypothesis on how that happens.
We have one more question from the peanut gallery here. It's a great one too, from Henry Kluzik. He says, a question about a question: has attention been paid to the possibility and limitations of detecting extrasolar CMEs from other stars? So, for example, could Voyager 2 detect both solar or extrasolar CMEs, or would CMEs just really kind of disperse too much and there wouldn't be anything left of them to detect? But a great question. I love that.
Yeah, that's a fantastic question. And actually, there are people that do that. So there are stellar astronomers that study stars, and it's actually not that difficult to see, because what happens is these CMEs, these events are so strong that that if you're watching, one of the things that the astronomers study are the light curves, and so this is how the emission of a star, the light coming from a star, changes as a function of time. And so what happens if you have a flare or a CME, that emission is going to spike up, and depending on how much that emission spikes up, gives you an idea of how strong that CME or that flare on that star is. And so there are actually quite a few stellar astronomers that do study these. And one of the things that we have learned from doing this is that the sun, although it is able to produce these massive stars, it's not nearly as active or as bad as it could be. There are stars that are popping off these CME class solar storms, every couple of minutes or every couple of days. And so we're very fortunate to have this nice, quiet, boring star to rotate around because it would be tremendous impact on us. And actually, one of the interesting theories about these solar storms, these CMEs, they allow a large amount of radiation when they occur, a large amount of radiation to come down here on Earth. And so one theory is that when these extreme solar events happen, you have an increase in genetic mutations that kind of sparks a little bit of an evolutionary bloom almost. And so you'll tend to see manifestations of new, variations of species and things like that occur in the historical record. And we think that these might be tied to some very large storms in the past. But yeah, absolutely, there are stellar astronomers that are studying them. Not only can they see these storms occurring, but one really interesting area of study is looking for dips in the light curve. And as most of you might know, this is commonly how they detect exoplanets, right? If a planet moves in front of the star, you're going to have a little dip in that light curve, and depending on exactly how that light curve evolves, kind of tells you a little bit about that. But that same technique can also be used to detect star spots. So instead of a sunspot, a star spot, or active regions on another star. And so it's really interesting to kind of study the other stars and get a sense of what's going on there. And there's really kind of almost like two distinct populations of stars. There's stars that are very, very active, and there's stars that are just dead as dirt. And then the sun kind of exists in this region that's kind of in the middle. And so, that's another question that, solar physicists are looking to answer is, are we in this transitionary region where we're going from a more active state to a less active state? I should also mention that activity on other stars is tied to the depth of the convection zone. And the depth of the convection zone is related to the size of the star. So the very smallest stars are almost entirely entirely convective zones. As they get bigger, they'll start to have a core or a radiative zone. And so as they get even bigger and bigger, that convection zone shrinks in size relative to the size of the star. So you get smaller and smaller. So Earth is again, kind of right in that middle point. Our convective zone is about, for the top 0.25 solar radius, the top point, 0.3 solar radii, something like that. But again, there's stars that are fully convective, and we know that they have activity. And then there's, stars that, have, shallow convective zones, and they have activity. But try to understand, how all of that fits together is definitely a very interesting area of research for the sun.
That was great. Thank you. Thank you, Dr. Upton.
Absolutely.
That was wonderful. Yeah, that was much more. Yeah. Thank you, Franco, for making that happen. So that's a home run.
Thank you for coming with us. Wonderful.
No.
I have a question.
Oh,
Sure.
good.
If you'll remember, a few years ago, we had the big solar eclipse here, and that happened as we're approaching solar minimum. So there weren't very many sunspots, and the corona wasn't very interesting. Well, next one's in 2024, and that's approaching solar maximum.
Yes.
So I would imagine it's going to be a little more interesting. There should be a lot more detail in the corona and some sunspots.
Absolutely. So one of the things, unfortunately, with an eclipse, you're kind of blocking out the surface of the sun, and so you can't really see all the sunspots. But what you can see is the corona. And so, if the last solar eclipse, you probably noticed that it was very dipolar. You saw all these strands coming out of the top and a bunch of strands coming out of the bottom. And so, near solar maximum, the global magnetic field gets into a much more tangled configuration, and you get dipoles and quadrupoles and hexapoles. And so depending on how all the active regions are positioned on the sun, you'll get, kind of like, loops kind of coming off to this side and another loop coming off to this side. And so you'll get a much more complex configuration to those coronal streamers that you'll see coming off of the sun. So that'll be very interesting to see.
You had me at dipoles. I'm stoked. Can't wait for the next eclipse. I hope, because Shannon and Bob and I and a few others ended up in Cloudsville, and
oh, it's awful.
we saw it. I mean, through the clouds, but
that's good.
Yeah, so we did see it. We're gonna get a much better location this time, I think.
Great. Yeah, that's fantastic.
And one other thing, can you imagine if we spot a big CME coming our way and NOAA springs into action, we shut down big parts of the power grid, except Texas, and then it misses? Who pays that bill?
Well, like I said, I mean,
the control experiment, they will be the one that will prove what the scientists were saying.
I'm not sure people will see it that way.
Yeah, that's just idiocracy is what that is, Moshe.
Yeah, but again, these CMEs, they are very massive. Like I said, on the order of the size, they can get on the order of the size of the sun. So the other thing is that when they're coming at you, if you've got a satellite that's looking at the sun, when those solar storms are coming at you, you get inundated with photons. So they call it snow on the solar snow, because when these solar storms are coming directly at you, the intensity just saturates everything, and it almost looks like one of those, those back in the olden days, you had your black and white TV, and they'd have the just the snow on the screen where it's just speckled, and so it's just this inundation of this snow. And so I think that the chances of that happening are pretty unlikely. I mean, I guess if it was like a grazing kind of thing, but I think if it was a grazing kind of thing, then it's not going to have as big of an impact. It wouldn't be likely to have as big of an impact. As I said, it's all about the orientation of the magnetic field. And so to really have a big impact, you need to be directed right at Earth. That magnetic field orientation has to be just the right way. And I think if it's more of a grazing event, it's not going to be as severe. So I don't think that we have to worry about that too much.
Anything that's viewable or special? I mean, the eclipse that's coming in June is a partial. It's going to be at 5 in the morning. It's going to be just after sunrise. from an observer's perspective, anything that might be interesting other than the event itself?
Well, as Franco showed in his pictures, sometimes when you have these types of events, you can really get some stunning views of the prominences kind of peeking off of the edge of the sun. So I would look out for those. Again, looking it's such a great opportunity to see a part of the sun that we don't normally get to see, this corona, because the corona is just it's so faint in comparison to the rest of the sun that normally, if you're looking at the sun, you're not going to see it. I don't know how well you'll be able to see it in a partial eclipse, though. So I would think maybe try to look towards the limb and see if you can capture some prominences. Being in June, we're still at we're just barely coming out of solar minimum, so not a whole lot going on in the sun these days, but. I would definitely suggest that maybe a few days or a week beforehand, take a look at the NOAA's website, the Space Weather Prediction Center. There's also a fantastic website called The Sun Today, and if you just Google that, The Sun Today, it will pull up all the latest images from SDO. SDO is our top-notch satellite that's observing the sun right now. And so it's got a suite of instruments that's observing in all kinds of different wavelengths, producing some just absolutely stunning pictures of the sun. And so if you want to kind of get a sneak peek of what to expect beforehand, I would definitely check out, SDO's images a few days or a week beforehand to see what you might have in store. And if you see some active regions that are closer to the limb, it's possible that you might get some really nice prominences or be able to capture some coronal loops going off the side of the sun or something like that.
Yeah, I use spaceweather.com too. That's
that's a fantastic website as well. Yeah, I think I just did an interview with them last week.
Yeah, they're really good. I think that what they post up there, but everything you listed is wonderful, and people that study this and guys like Franco and everybody else that's taking pictures of this stuff just makes me want to take out. We've got a nice lunch too, so I want to take that out when I get back up there. I want to look at the sun some more. I like it.
Absolutely, man. Franco, your images again. I mean, just absolutely gorgeous.
He got better. He got like exponentially better when he got his gear back. Yeah. So it really, it looks really good. It's
very
excellent
much
now.
Enjoyed that. You got great pictures of
the. We hope that you're gonna come and visit again. Who knows, to give us an update in a year or so.
Sure, I'd be happy to. Yeah, just let me know.
Great. We so enjoyed your lecture.
Let's wrap it. So next month, Thierry Legault will be with us, and we do hope to open up the observatory. Fingers crossed that we can do it in May. I hope that we can do that for public nights soon. Yeah, fingers crossed. I really want to see people looking at the planets again. But that's it. Is there anything else to add here, guys?
I don't think so.
Just a fantastic lecture. Thank you. Thank you.
That was good.
Thank you very much.
Yeah, we'll see you. We'll see you all next month, and we'll stick a fork in this, and we'll see you soon. Thanks, everybody.
Thank you.
Thank you.
Bye-bye.